Ladies and gentlemen, welcome to Circuit Protection Terms and Principles. So, our topic today is about circuit protection, as it says. Some of the principles that underlie circuit protection and some of the terms and definitions that we use in this topic. Obviously, this will not be the first time that you've heard of this. I think, in fact, for the remainder of our course, all of the topics that we do will be things that you've come across before, that we've at some stage we would have done something or talked about in some sort of capacity before. So hopefully nothing will be massively new to you. We can see on the front page here, what do we have? A selection of circuit breakers. Circuit breakers over here. RCDs here. How do I know that's an RCD? Well, because it's got a test button there. And we have a variety of HRC fuses here, HRC fuse links. They're lovely looking. Okay, what is circuit protection and why do we need it? A circuit protection device automatically prevents dangerous or excess amounts of temperature, excessive amounts of current or a short circuit in an electrical conductor. The device needs to respond rapidly so that it limits the amount of energy that can occur in the event of an electrical fault. Okay, what's it for? Right, so we know this one, right? We know this one. When a circuit draws too much current, that can damage the conductors, the cables, and the fittings that are attached to that circuit. In particular, the conductors, right, the cables, because if we allow an uninterrupted overcurrent in our circuit, then if it kills an appliance, it kills the appliance, and your appliance is broken, you have to get another one. Sad. If it kills a cable in the wall, well, one, that means that somebody's got to replace that. That's not an easy or cheap proposition, right? Because someone's got to pull the cable out of the wall and put a new one in. Secondly, that could cause significant damage, right? It could cause fires if that cable overheats inside the wall or in the ceiling and breaks down and burns, then it's going to cause a fire. Could potentially cause a fire, which is obviously going to result in a significant amount of property damage and potential injury or death to people. So we have our circuit protection to automatically cut off the supply when it detects a fault. How does it know that there's a fault? Well, we place a limit on that protection device. We say we're going to install a protection device that will stop, that will turn off once current exceeds a certain amount. And then everything after that circuit protection, we ensure that the current carrying capacity or the ability for that conductor, fitting device, whatever it is, to draw current or to supply current is greater than the maximum breaking or cut off current of our protection device. No, that makes sense. That's fairly obvious. All right. So we need to talk about what it says in our standards, right? So ASNs, we're referring here to ASN ZS 3000, and we're referring specifically to clause 2.4.2, protection by automatic disconnection of supply. What does it say? Protection by means of automatic disconnection of supply is intended to limit the prospective touch voltage arising between simultaneously accessible conductive parts in the event of a fault between a live part and exposed conductive parts or a protective earthing conductor. This protection shall be achieved by provision of a system of earthing in which exposed conductive parts are connected to a protective earthing conductor in accordance with section 5, and disconnection of the fault by an overcurrent protective device or an RCD. Right, what does this mean? What does it say? Okay, so we talked about disconnection of supply, or our protection devices. I just talked about them being devices for protection of primarily for protection of our conductors and fittings in order to stop those things happening, fires and so forth. But what we've got here is what happens when there is a phase to earth fault in an appliance, for example. If there's a phase to earth fault, as in the phase wire comes off and it's touching the earth, the metal body of my appliance, well then if I go and touch that, I get a shock, right? You know, the current will flow through the phase through into the body of the appliance, and then I touch it, and then the current is going to flow through me back to earth. I complete the circuit and I might die, or at the very least I get a nasty electric shock, and that's not much fun. So then our protection device here, if we're not talking about RCDs, what's going to happen? Well, every piece of metal on that appliance should be earth, right? It's connected to the earth conductor. Earth conductor goes all the way back to the switchboard and it's connected to our neutral. So when my phase conductor falls off and it touches the body of the appliance, then current should flow down the phase through the body of the appliance to the earth conductor, which is connected to the body, back down the earth conductor to the switchboard, to the earth buzz bar, which is linked to the neutral buzz bar. So it goes across that link into the neutral. That completes the circuit, and I get a very high current flow because there's not much resistance, right? That conductor's fallen straight off and gone onto the metal body, so there's almost no resistance. Because there's almost no resistance, we'll then have a very high current flow in that circuit, and therefore the circuit breaker or fuse or whatever it is turns off. And that way, that's now actually protecting, it's not protecting the conductor from an overcurrent, that's protecting me from getting that electric shock. The theory is as soon as that conductor falls off inside the appliance, or however that happens, that the phase wire contacts the body of the appliance, it's going to trip that fuse immediately because that high current will flow. Before I get a chance to go and touch that appliance and get a shock, it's immediately going to disconnect the supply. And then what happens? Well, then I go, that's weird, my thing's not working. I go back to the switchboard, I flick it on, immediately we get that high current to earth again, switches itself off. I go, something happened, something weird happened there. Unplug that appliance, go back to the switchboard, switch it back on. Cool, everything works. Plug my appliance back in, trips the circuit breaker again. Okay, there's something wrong with my appliance. But at no time have I actually got a shock or even been in danger of having a shock, because every time I turn the power on or plug that appliance in, trips straight away because of our earthing system. So that is what this section here, 2.4.2, is telling us. That's what the crux of this guy here is. If we have a proper earthing system and we have proper protection devices, then that will protect us from faults, earth faults within appliances, fittings, whatever it is. Right, 2.4.3. So again, this is 2.4.3 paragraph in paragraph 2.4.3 of ASN ZS 3000. Types of devices. A device used for protection by automatic disconnection of supply shall not be capable of automatically reclosing. The following types of devices may be employed to provide automatic disconnection of supply. We have closed fuse links, miniature overcurrent circuit breakers, molded case circuit breakers, fixed setting RCDs, other devices having characteristics similar to the devices listed above. Semi-enclosed rewirable fuses shall not be used. Okay, let's address those one by one. The first thing there, should not be capable of automatically reclosing. Okay, we have talked about automatic reclosing in terms of electricity supply, right? So supply to power lines. We've mentioned before that sometimes those will reclose automatically. But in terms of your day-to-day stuff covered by ASN ZS 3000, normal low voltage installations, there must not be any ability for that to automatically reconnect. Once it's disconnected, and then somebody has to go and manually reset it. Or manually reset it in the case of a RCD or MCB, but actually by changing out the fuse link in a HRC or something, right? So the types of things we can use, enclosed fuse links. So that's talking about like a HRC fuse link that's put into a fitting, into a holder, and that goes into the enclosure. A miniature overcurrent circuit breaker, so a normal MCB that we would come across. Molded case circuit breaker, essentially the same thing as an MCB. It's just bigger. It's not really it's not really necessary to differentiate between them. They're just circuit breakers. D, a fixed setting RCD. Well, we know what an RCD is, and we understand that why we would use that and where we would use that. The only interesting thing there is that it's a fixed setting. There are such things as adjustable RCDs, but what we're saying is that for the purposes of ASN ZS3000 and the protection devices that we would use, that we would not use adjustable RCDs, because then that means that people can go and fiddle with them, right? And then maybe it trips off all the time because actually something in the house has an earth fault, and they go, oh, this is a pain, I'll just change the setting so it doesn't trip. Well, no, we don't want that to happen. And the last one, other devices with no automatic reclose function having character, yada yada. Look, I don't know what those are, but essentially it's giving us a method there that if there is some other device that will do the same job as those ones above, that we can use that if we want to. Semi-enclosed rewirable fuses shall not be used. Well, that's a good idea. Rewirable fuses are not used anymore. Doesn't mean they don't exist. They do exist. It does not mean that you cannot replace a fuse wire. You can, but you cannot install a new rewirable fuse. I would certainly recommend that if you ever come across a rewirable that needs to be replaced, as in the fuse is blown, you can buy plug-in circuit breakers. Plug-in circuit breaker. So this is something that will, in the rewirable fuse base, you just take out the fuse holder, throw it away, you get a plug-in circuit breaker and you plug it into the fuse base, and it acts like any other normal fuse circuit breaker. It's a great option to replace a rewirable because it doesn't require you to replace the base at all. It doesn't require you to disconnect any wiring or anything like that. Just pull out the rewirable, put the new one in. And the first time I moved into a house that had rewirable fuses, I did eventually replace the switchboard in that house with a new one, but initially I just replaced the rewirable fuse holders with the plug-in circuit breaker replacements. Yeah, very simple. They cost, I don't know, I think they were about $30 or $40 back then, which seems like a lot of money, I suppose, but when you think about what you're saving yourself, it's not a bad little price. They may even be cheaper than that. I can't remember. It's been a long time since I've used one. Alright, let's have a look at some terminology. Current rating. What does the current rating of a circuit breaker mean? Well, or a fuse rather, fuse or circuit breaker. That's the maximum current that a fuse or MCB will carry continuously without overheating or deteriorating. Voltage rating. The maximum voltage that a fuse or MCB is designed to withstand without insulation breakdown. Remember that current affects our conductors and voltage affects our insulators generally. So our voltage rating is the rating of the insulation, the internal insulation inside that circuit breaker or fuse before it starts to break down. Current rating is the maximum current that will carry continuously. It's not the same as the fusing rating, or it's not the same as the prospective short circuit current or breaking capacity, like the maximum amount of current that it can successfully trip. Just means that the maximum it can carry continuously. The fusing current is the minimum current at which a fuse element will begin to rupture. So this is specifically for a fuse, not for an MCB, but the minimum current at which a fuse element will begin to rupture. So if you think about a fuse element, at its essence is just a piece of wire, and it's going to disintegrate when you get an overcurrent. So the fusing current is the minimum current before it starts to fuse. Okay. Fusing factor. Fusing factor is the ratio of minimum fusing current to its current rating. Let's have a look. Okay, let's have a think about this for a minute. The minimum fusing current, so that's the minimum amount of current that it starts to fuse at, and then the fuse current rating is the maximum current that it will carry before it completely breaks down. So this is basically the minimum current that it'll trip at, divided by the maximum current that it'll trip at. So the smaller that figure, I mean, it can't be any smaller than 1, right? Because the minimum fusing current has to be less than the maximum fuse current, basically. So it couldn't be more than 1. But if it was 1, then we don't have much leeway, right? If our minimum fusing current, let's say, is 20 amps, and then our fuse current rating is 20 amps, that means at 19.9 amps, everything is fine. At 20.1 amps, the fuse is blown. As soon as we go over 20 amps, it's going to blow. We probably don't want that, because every now and then we might get a little spike, and we don't want to blow the fuse every single time. We get a little overcurrent. So our fusing factor probably doesn't want to be 1. Wants to be a bit higher than 1. What we can say about this, and you need to know this, so remember it, is that the fusing factor is proportional to the minimum fusing current. Because if I increase this number here, then the fusing factor, the answer to this equation will go up. Right, so if my minimum fusing current is, let's say, 20 amps, and the fuse current rating is 40 amps, then my fusing factor must be 0.5, 20 divided by 40. But if the minimum fusing current went up 30, then 30 divided by 40, fusing factor would be 0.75. So the fusing factor is proportional to the minimum fusing current. And therefore, the opposite is true of this. The fusing factor is inversely proportional to the fuse current rating. So again, if I had minimum fusing current of 20 amps and the fuse current rating was 40 amps, so the minimum current at which the fuse will blow will be 20. The maximum current at which the fuse will blow is 40. That means 20 divided by 40 is 0.5. If I move the fuse current rating down, if I bring that down to, let's say, 30, then 20 divided by 30 is like 0.66, right? It's 2/3. So that means that as my fuse current rating goes down, the fusing factor goes up. Or if the fuse current rating goes up, the fusing factor goes down. That's just mathematically true because the fuse current rating is on the bottom of the divided by line. So every time this goes up, the answer goes down. So it's inversely proportional. Fusing factor is inversely proportional to the fuse current rating. Right, we all got that? Okay, let's move on. And tripping factor. Guess what? The tripping factor is the ratio of minimum overcurrent that will trip an MCB to its current rating. Sound familiar? Yep, it's exactly the same as the last one. What's the difference? Well, now we're talking about an MCB. That's the only difference. The tripping factor refers to an MCB because that is a thing that trips, a circuit breaker, because it trips. Fusing factor refers to a fuse because it's a fuse. But tripping factor and fusing factor are the same thing. They're just, one refers to a thing that trips and the other refers to a thing that fuses. So our tripping factor is the minimum tripping current divided by the rated current, or the maximum. The rated current being the maximum amount of current that it will carry until it fuses, or until it trips, rather. So that means, again, listen carefully, the tripping factor is proportional to the minimum tripping current. That means when the minimum tripping current goes up, tripping factor goes up also. Tripping factor is inversely proportional to the MCB current rating. If the MCB current rating goes up and the minimum tripping current does not, then the tripping factor will go down. So if MCB current rating goes up, tripping factor goes down. If MCB current rating goes down, tripping factor goes up. This means that the the tripping factor is inversely proportional to the MCB current rating. Right, got it? Let's move on. Okay, the next definition, cutoff characteristic. Cutoff characteristic. The cutoff characteristic is a measure of how quickly a protective device can interrupt a short circuit current as it rises in the circuit. Woo. That's a mouthful. Note, a quick cutoff characteristic limits the energy input to the fault, thereby reducing electromechanical and thermal stress in the electrical system to a minimum. Okay, what does it all mean? What does it all mean? Basically, it means how fast does the device trip? If I reach my rated current, the maximum amount that my circuit breaker or fuse will blow at, how quickly does it operate? Well, what do I want here? What is this? Why is this important? Well, the faster that it operates, then the less time that current is hanging around in my circuit. So as it says here, we reduce the amount of electromechanical and thermal stress. So we're just reducing the amount of time that the current is operating in the circuit. So we're reducing the amount of damage that it can do. So we have a little graph here. Look, there's at this point here, we've got the start of our short circuit. Up here, we've got our cutoff point. This is our current going up and our time going left to right. So the shorter that time period, in other words, the steeper this initial line, the faster it's going to cut off. Okay, so in this case here, it's showing we've got what have we got there? The old sine wave there. We've all seen that before, right? We know what a sine wave is. Looks a bit odd, doesn't it? We've got a big hump on this side and quite a small one on that, so I'm not sure why they've drawn it like that. But we have we have one cycle, 0.02 seconds. It says it there, that's the time that one cycle would take in a 50 hertz system. And then we can see as the current starts to come up, then it's going to trip about there, which represents, it doesn't say how much time, very short amount of time. And then we have our arcing time. So that's, although the device is operated, remember we've talked about when we disconnect the current, we always get a little bit of arcing as the terminals come apart. We're going to get some arcing. So this is our arcing here, arcing time from there to there, and that's our current trace. So that's the current is slowly dropping away as the gap between the contacts get wider, and then the arc gradually dissipates. It's no longer able to maintain an arc, and therefore current flow cuts off. And so that would be from the time it starts to trip until the time the arc is extinguished. That's our total clearance time. There we go. And that is our cutoff characteristic. Cutoff characteristic is how fast will our device operate once it reaches that overcurrent condition. Next one is time current characteristic. Time current characteristic. As current through the fuse or MCB increases beyond its normal current rating, its operating time decreases. This is called the inverse time current characteristic. So what we're saying there is on the last one we saw the cutoff characteristic. How fast does it operate? This one here is basically saying that operating time will decrease the higher the current is. So we're going to have a cutoff characteristic for whatever the rated current, but the cutoff characteristic at 2 times the rated current is probably going to be different. It's going to operate faster. That is the time current characteristic. If we look at the diagram here, we've got motor starter, overload relay, and HRC fuse link. Pre-arcing time of the HRC fuse under short circuit condition, that's here, discrimination, backup protection, yada yada yada. So we have the current, and then on this axis here is going to be time. So at a small overcurrent, it's going to take a long time for that to operate. Then as the current increases, our time to operate comes down. And then, well, we've got an overlap there with our secondary protection. But nevertheless, this shows us that as that current is increasing, so we're going left to right, current is increasing, then the time it takes to trip that device goes down and down and down. And then same with this device here, it's another device, but as that current, it takes a little bit longer for that device to trip, but when it does reach that current, then the time taken for it to trip gets lower and lower. So there's the time current characteristic, so inverse time current characteristic. The greater the current is, the faster the device will operate. Yeah, that makes sense, right? That's pretty obvious. Okay, next one is discrimination. No, it's not something where we're mean to people who are different gender or race to us. Discrimination in terms of circuit protection is a good thing, right? So discrimination means when a protective device operates on a fault, the supply is interrupted and localized at the faulty circuit only, leaving the good circuits ahead of it unaffected, right? So that means, in a nutshell, and I think I have said this to you guys before, what that means is when we get an overcurrent, we want the protection device closest to the fault to operate, right? If I short something out sitting here on my laptop, I want the circuit breaker in my switchboard that is protecting the socket right here to operate. I don't want the main switch. I don't want to say them. If there was a main circuit breaker, I won't have a main circuit breaker. If there was a main circuit breaker in my switchboard that controlled the whole house, I don't want that one to operate because it's going to turn off my whole house. If I've got fuses out at the mains connection point out on the street, I don't want those fuses to blow. There may be a fuse, or there will be a fuse at the transformer somewhere down the street on top of a power pole. I don't want that to blow either. That would be crazy. Then I'm going to take out the whole street. So discrimination is that the lowest protection on the circuit, or the closest to the fault, is the one that operates. And we do that by having gradually larger circuit breakers, right? So the smallest one is closest to the end, and then the next one back is bigger, and the next one back is bigger. If we go back to the previous slide, you'll see this is a type of discrimination in here, right? So that at this amount, it says it right there, discrimination here. So at this amount of current or lower, only this device, the motor starter overload relay, will operate. Once we reach this amount of current, then this one is going to operate, right? So that one has a faster tripping time at that amount of current. So once we hit that amount of current, the HRC fuse is going to blow before this one. But that one there gives us some discrimination, so that at lower fault currents, our device that's closest to the fault will trip first. Okay, so we have a fair bit to cover on discrimination. Probably the next 10 to 15 minutes are just talking about discrimination. So we will take a short break there. I will come back to you shortly. As ever, you will need a code for the quiz. So let's say that the first two digits of our code for this one will be 12. That's 12. 12 will be the first two digits of the code for this test. See you shortly.